hazmat. And it has also been shown that in days which the concentration of ozone is increased, it also increased the number of internations hospitals by respiratory infections. And it's also been shown that in aged mice, when exposed to ozone, there's a delayed wound healing, but there's no study about the respiratory effects. There's also been shown in the literature that TNF-alpha is increased with increasing age. And it's known that TNF-alpha is induced by ozone exposure, and that's required for airway hyperresponsiveness and inflammation. So the work of the lab is mainly trying to figure out if there is a difference of response and if the TNF-alpha plays a role. The methods were, there were 42 mice. They were wild type and TNFR1 deficient. TNFR1 is a receptor for TNF-alpha. And they were 7 weeks or 32 weeks old. And half of the mice were exposed to ozone, 2 ppm for 3 hours, and half of them to air. 4 hours after the exposure, the bowel was collected and the tissues harvested. The results from the lab shows there is a increased inflammation with ozone exposure in all groups. But what's interesting is that in the wild type group, with the 32 weeks old mice, they have less inflammation than the 7 weeks old. And when we took out the TNFR1, it's actually reversed. So maybe the old mice, when exposed to ozone, have a protective factor against inflammation, and it can be because of the TNF-alpha. So it's in that stage of the study that Lucas and I came in, and we studied some genes, the expression of some genes to figure out why is this happening. So MT1, MT2, it's metallothionein 1, 2, and oxygenase 1 are 3 antioxidants, and they are highly induced to ozone exposure. And they've been shown that by other stimuli, you can induce these genes, and it requires TNF-alpha. And the increase of these proteins is responsible to decrease the inflammatory response to ozone exposure. So, to measure the expression, we learned how to design primers, and we extract RNA from the lungs of the mice that we had. And we made cDNA from that RNA, and with the primers and the cDNA, we ran real-time PCR. The data from this study shows there's highly expressed in the ozone in all groups, but it didn't show any differential between the wild type and TNFR1. It was not what we were expecting. So we looked at another gene, amphiregulin. Amphiregulin is from the epidermal growth factor family, and it's induced by ozone exposures as well, and is induced by TNF-alpha. And a recent study had shown that it decreases lung injury. So maybe this gene can play a role. So we use the same methods, and it's also highly induced by ozone, like we found in the literature. And here, in the group that we had less inflammation, we found that, a greater expression. So this could really mean something. That could really be one of the genes that explain this important role. But we measured also another gene, Claudin-4. Claudin-4 is impacted by TNF-alpha, and it's a part of the tight junctions of the cells, and plays an important role in the epithelial barrier function in the alga. And in that study that the lab has done, it's been shown that the TNF-alpha deficiency plays a role in the lung epithelial integrity. So, when we have the TNF-alpha deficiency, we found more bell protein. So the barrier is not so injured. So we did the same thing, but we didn't find any difference between the groups, the wild type and the TNF-alpha. But one nice thing is that this gene has never, at least we didn't find in the literature, it was never shown that it was induced by ozone. And here, in all those groups, we can see that it's highly induced. So from now on, we plan to focus on antiregulin. It was the gene that showed us that difference that we were expecting, and it maybe can really explain what's happening. And antiregulin is well studied in cancer genesis, and there's a lot of drugs that can actually block the receptor for antiregulin. So probably that's the path that we're going to take to assure if the decrease of inflammation comes from the increase of antiregulin.